Hello everyone, this is a quick and basic explanation of particle physics, particularly the standard model, using the 3D animation software Blender. Links in the description. Particle physics is the study of small, usually subatomic particles and how they interact. Though there are many particles, I will only talk about the standard model ones, which link matter and force particles in an attempt to explain aspects of the subatomic and the universe itself. It does not explain general relativity and gravity, universal expansion, dark matter, matter-antimatter asymmetry, and some properties of the neutrino.
But Zach, what about that banana particle?
No, Max, there's no particle based on the yellow edible berry fruit. The two particle categories are fermions and bosons. Fermions have half spins like 1/2, -1/2, and 3/2, and are matter particles, while bosons have integer spins like 0 and 1, and are energy and force particles. Simply put, spin is the angular momentum that corresponds to a particle, like density to a substance. 1/2 spin particles need to rotate twice to return to original positions, while spin of 1 particles rotate once to return to original positions. Atoms are made up of protons, neutrons, and electrons, or antimatter counterparts, indicated by a line over the particle initial. However, protons and neutrons are made up of fermions, known as quarks. If we ignore color change, there are 12 types of quarks, all with spin 1/2, which come in 6 flavors. These are up, down, charm, strange, top, and bottom. Each have a respective anti-quark and 3 generation labels which divide them into pairs. Up, charm, and top have positive 2/3 of elementary charge, and down, strange, and bottom have negative 1/3 of elementary charge. 2 up quarks and 1 down make a proton, and 2 down quarks and 1 up make a neutron. However, the quark mass is a small portion of the proton and neutron masses. Rather, the condensed energy in protons and neutrons make up most of the mass. Under high energies like in fusion, up can become down plus a positron and an electron neutrino, while down decays into up plus an electron and an electron antineutrino, which is consistent with neutron and antineutron decay, though down quarks are more stable in hadrons. The second and third generation quarks are much heavier, thus less stable, and are more uncommon. These quarks are created through high energy collisions. They can form particles of 2 or more quarks known as hadrons. They are like up and down quarks, but typically decay into up or down quarks. Top quarks have a mass around the same as rhenium, so they are incredibly unstable. To follow suit, bottom quarks have a mass similar to helium, and charm quarks have a mass similar to hydrogen. The lighter strange quarks can form strangelets under higher pressure with up and down quarks. This strange matter is hypothesized to be more stable than our nucleons, so they are converted into strange matter. There's a hypothesis expressing that once in contact, strange matter would shrink the Earth as it would convert all Earth's matter into strange matter. However, there is no strong evidence for strangelets to pose a danger to us. With color change, there are 36 total quarks. Each quark can be red, blue, or green, while antiquarks can be anti-red, anti-blue, or anti-green. Just like in optics, if all 3 colors are mixed together, or an anticolor is mixed with its correspondent, the particle is white or has no color change. Being colorless means that the strong nuclear force holds the quarks together. Leptons are fermions, but unlike quarks, are not affected by the strong force. These also come in 6 flavors in 3 generations. The flavors are electron, muon, tau, and neutrino counterparts. Additionally, these come with corresponding antimatter counterparts. The neutrinos have no charge, but the others have negative elementary charge. Electrons are the lightest of the charged leptons and are stable. Muons are about 1/10 of a hydrogen atom in mass, and tau are about 2 hydrogens in mass. Both are very unstable. Muons are created from cosmic ray collisions, and they decay into electrons, electron neutrinos, and muon neutrinos. They can replace electrons in atoms and can even replace the nucleus of atoms, temporarily creating muonium. Muons penetrate deeper than X-rays and gamma rays, so they can be used for imaging and radiography. Tau are similar to muons, but since they're more massive, they're more unstable. They are unique in that they can decay into hadrons as well as muons or electrons. Like the electron neutrinos, muon neutrinos and tau neutrinos come from decaying muon and tau particles respectively. The other type of elementary particles are bosons, and there are 2 types, gauge bosons and scalar bosons. Gauge bosons have spins of 1, while scalar bosons have 0 spin. Gauge bosons are virtual force carriers controlling strong, weak, and electromagnetic forces. Virtual refers to the particles being temporarily propagated as the quanta of a field. These kinds of particles do exhibit some qualities similar to real particles, like momentum conservation. Gluons are the particles that act as the exchange of strong force between quarks, holding them together like glue. They are responsible for quark color change, and there are 8 in total. Each one carries the appropriate colors to change quark colors, causing the strong force. Photons, typically depicted as quantized energy packets moving at the speed of light, can manipulate the electromagnetic force without being affected. Unlike their counterparts, these photons are virtual and do not emit light. Unlike the other two, W and Z bosons have mass and correspond to the weak nuclear force. W bosons come in W positive and W negative, which are both antiparticles of each other, and have charge of plus or minus 1 elementary charge, while Z bosons are neutral. W bosons have mass similar to cobalt, and Z bosons close to ruthenium, limiting the range of the particles, unlike photons. The W bosons correspond to the release and absorption of neutrinos, while Z bosons correspond to momentum, energy, and spin conservation from neutrinos. In neutron decay, the second down quark is converted into an up quark and a negative W boson. This acts as an intermediate to turn into an electron and an antineutrino. Positive W boson does the same process but for anti-neutron decay. Conservation of charge, momentum, and energy all occur here. Z bosons decay into a fermion and its corresponding antiparticle. Similar to photons and electromagnetic interactions, Z bosons do not change charge or mass of the particles and carry momentum. The only scalar boson in the standard model is the Higgs boson, so it has zero spin and even parity, or that it is unaffected by direction changes like a scalar quantity. The Higgs boson is a virtual particle theorized to explain mass generation in particles of mass, especially the W and Z bosons. The Higgs field supposedly exists throughout the universe, and the Higgs bosons from it interact with certain particles to give them mass. However, the energy around quarks makes up most of the mass of the protons and neutrons. Higgs has a mass around cesium and quickly decays into either quark pairs or bosons.